Hello, everybody, and welcome to our session on SQL Server 2022 goodies. Today, we're going to focus on a few sweet things that we've added to SQL Server 2022 that will improve reliability and make developers' lives writing T-SQL easier. My name's Kendal Van Dyke. I'm a senior program manager on the SQL Server team. I'm joined by my colleague, Perry Skountrianos. Perry, tell us a little bit about yourself before we get started.
Thanks, Kendal. Hi, folks. My name is Perry Skountrianos, and I'm currently one of the SQL Server PMs in the SQL Server team. I joined Microsoft in October 2014, and I'm currently focusing on SQL Server engine features, availability, and performance. Kendal?
Thanks, Perry. My name's Kendal Van Dyke. I've got 23 years of IT experience spread across different disciplines as a dev, a DBA, a consultant, and most recently a PM. I joined Microsoft in January of 2016 and joined the SQL Server team last year in July. And I focus on high availability, disaster recovery, and performance. Now, for today's session, we've got something for everyone. For administrators, we'll take the first half to talk about T-SQL snapshot backups and improvements to accelerated database recovery. And for developers, the second half of our session will cover enhancements and new features to the T-SQL language in SQL Server 2022. So let's get started. Perry, over to you.
Okay, so let's get started with the new T-SQL snapshot backup feature in SQL Server 2022. This feature is targeting our developers in the audience that would like to develop their own simple cross-platform SQL snapshot backup solutions that can run both on Windows and Linux. As you know, databases are getting larger and larger every day. Performing streaming backups is a size of data operation and can consume resources, CPU, memory, I/O, network, which impact the performance of the workload for the duration of the backup. One way to make the backup a constant operation rather than size of data operation is by performing a snapshot backup using mechanisms provided by the underlying storage or service. In the past, users have relied on third-party solutions that were built on top of the SQL Writer service to complete snapshot backups. The SQL Writer service depends on Windows VSS, the volume shadow service, along with SQL Server VDI, the virtual device interface, to perform the orchestration between SQL Server and the disk-level snapshot. Because of these dependencies, backup clients based on the SQL Writer service tend to be complex, and they only work on Windows. With the introduction of T-SQL snapshot backups, the SQL Server side of the orchestration can be now handled with a series of these new T-SQL commands that I'm going to show you shortly. This allows users to create their own simple cross-platform backup applications or even scripted solutions if the underlying storage supports a scripting interface to initiate the snapshot. So let's take a look on those new T-SQL commands. You start by suspending the database that you'd like to perform a snapshot backup on. You use this command, alter database name, set suspend for snapshot backup on, and that command will acquire the database logs, will invalidate the differential bitmaps, and will freeze the database, still allowing reads but suspending writes. Then the user initiates and performs the actual snapshot backup. This operation needs to be fast, ideally less than a second. One way of doing that, if you're running SQL Server in an Azure VM, is by using the AZ snapshot create command that will create a snapshot of the underlying disk used by the VM. Finally, we have to back up the metadata of the database in this new BKM file. We use the backup database name to disk, this BKM file with metadata only, and that will unsuspend the database, record the backup, and release the backup logs. Here's an end-to-end snapshot backup sample script. So the user starts, as we saw, by suspending the database, alter database, AdventureWorks, set suspend for snapshot backup on. SQL Server will acquire the logs, invalidate the differential bitmap, and freeze the database. Return to the client. If that freeze failed, obviously the suspend is failed, you need to retry or end the script. If the freeze was successful, then the user needs to issue a script to generate the snapshot. When the snapshot is complete, the final step is to backup the metadata of the AdventureWorks database by using backup database AdventureWorks to disk BKM file with metadata only. And then that command will unfreeze the database automatically, record the backup success in backup history, reset backup chain for full backups, and return success to the client. Obviously, if the snapshot was not successful, the altered database AdventureWorks set suspend for snapshot backup off will unsuspend the database. So that was a quick introduction of how you can issue a SQL Server snapshot backup with these new T-SQL commands. So with that, let's go take a look at the restore. Restore is equally simple. You can use restore database name, using the BKM file with metadata only, specifying the original database name. You can also restore the database with a new name, specifying it here, that will use restore database, new database name from disk, this BKM file with metadata only, specifying the original database name. Next, I want to show you the equivalent end-to-end snapshot restore script. User mounts the snapshot. If the files are in the desired location, if they're not, we need to copy the files to the desired location by leveraging the move keyword. So restore database AdventureWorks from the BKM file with metadata only, and then we move the MDF and LDF file to the desired location. If they are in the desired location, then we want to decide if we want to apply transaction logs after the snapshot restore. If not, then we use restore database AdventureWorks from the BKM file with metadata only. If we want to apply log backups, then we restore the database with non-recovery. And then when this is done, we restore the log backups with recovery. With that said, we are introducing additional functionality with this new feature. One is you have the option to suspend the server to freeze all user databases and perform snapshot backups. So by using alter server configuration, set suspend for snapshot backup on, that will suspend every database in this server. And then you can backup server to this BKM file with metadata only. That will back up metadata for all these databases. Next, you can suspend multiple user databases with a single command. Alter server configuration set suspend for snapshot backup on a specific group of databases if you don't want to suspend all the databases under the server. And then you backup group testdb1, testdb2 to this BKM file with metadata only. Finally, you can perform copy-only snapshot backups. You can alter a database, suspend it with mode copy only. Then you backup database testdb1 to this BKM file with metadata only. And then you alter server configuration, set suspend for snapshot backup on, again with mode copy only, if you want to suspend all the databases under the server. And then you backup server to BKM file with metadata only. Perform a copy-only snapshot backup. Since the differential bitmap is cleared prior to freeze, we give that option to clear the differential bitmap prior to freeze. Finally, we're providing the following dynamic management views and properties to check the suspended status of the databases, logs acquired, and other useful information, including, for example, the suspend time that a specific database has been suspended for. And that will hopefully make it easier to manage and debug potential issues. So this is the sys DM server suspend status. Then using the sys DM tran logs, you have visibility on the specific logs that were acquired by the SQL Server when the database was suspended. And finally, these two server and database properties for recording the, taking a look at the suspend and properties of a database. So everything that I covered here for the T-SQL snapshot backup is covered through our publicly available documentation. That includes all the diagrams that I showed here, the workflows, along with the full list of the new T-SQL Server commands, along with a couple of more things like ways to tag the backup set, meaning that you can associate the actual snapshot backup with the metadata so you can easily know how to restore. And along with more links and getting started guides. So with that, that was the T-SQL snapshot backup feature in SQL Server 2022. Let's now switch gears to our next improvement called Accelerate Database Recovery, or ADR for short. This improvement has been in Azure SQL for quite some time, serving millions of databases, as well as in SQL Server 2019. ADR is targeting our DBAs in the audience who want to improve their SQL Server recovery and availability. Before we jump into the mechanics, let's go over the motivation for investing in this feature that greatly improves SQL Server recovery. Recovery time is proportional to the longest running transaction. Rolling back large batch operations like bulk insert takes a long time. Transaction log cannot be truncated during a long-running transaction. So in order to address these customer pain points, we had to re-architect the SQL Server recovery process from the ground up. So SQL Server database recovery process today is the process of reconciling the data, files, and the transaction log to bring the database to a consistent point in time. It consists of three phases: analysis, redo, and undo. During analysis, we determine the state of each transaction in the system at the time SQL Server stopped. During redo, we go all the way back to the oldest uncommitted transaction, and we return the database to the state it was in at the time the SQL Server stopped, and we open the database partially when redo is done. And finally, during undo, we scan the transaction log backwards all the way to the oldest uncommitted transaction, and we roll back any uncommitted transactions individually. When this is done, then the database is fully available for use. So SQL Server Database Recovery with Accelerated Database Recovery introduces version-based SQL Server recovery. The redo phase starts from the last successful checkpoint instead of the oldest uncommitted transaction. And the database becomes fully available after the redo phase. All the logs are released. ADR has four components that I want to cover a little bit in detail. The first one is PVS, the persistent version store, logical revert, slog, which is a special in-memory log stream, and a cleaner. So let's go take a look at these components in detail. First, let's start from the persistent version store, the PVS, which is a new SQL Server mechanism for persisting the existing versions generated in the database itself, instead of the original TempDB version store. And that has a lot of advantages. It enables resource isolation, and it improves the availability of readable secondaries. PVS has the following components: in-row, off-row, and version tracking and cleanup. So let's double click on those things and see how they work. Let's start with the in-row versions. In-row is a payload that is appended to the versioning information in the record, which allows the previous image of the row to be generated from the current image. So let's say if there is an update to a row and that delta fits into the record itself, we store it there, and we call that in-row versions. Let's take a look at the example of how that looks like. So on the left, we have a SQL example where we will store the full row in the data row, and on the right, an example where we store the difference. So imagine we are inserting the value read into table T1. This is how the data row looks like. The value is red, and then we have a version record pointer. And then on the update, let's imagine that we're updating the red to green. This is how the data row looks like. Green, version record pointer, and this we store the full row in row because it fits. That update was not large enough. In the case where the update is large enough and the full row does not fit in row, we calculate and store the difference in row. So the insert, this is how the data row looks like. When we update with a large update, the data row looks like this. This is the large update, the version record pointer, and the difference between these two updates. And we have the mechanism to revert to the previous version of the row using this difference. So let's move on now to the off-row version. Off-row version table is a persistent table that stores the previous version of updated rows. And it's very similar to the TempDB version store. So in the case where those updates do not fit in row, we use the PVS. And here's an example to better understand how that looks like. So let's assume there is an insert, the initial value. This is how the data row looks like. Then we update with a large update, and we push that version into the PVS version store. And if there is another update, we push that version in PVS as well, and we link those versions. Next, I want to move to the logical revert, which is the asynchronous process not run at undo, responsible for performing row-level version-based undo. And that provides instant transaction rollback. It keeps track of all aborted transactions, performs rollback using the PVS for all user transactions, releases all locks immediately after transaction abort, and performs user transaction rollback asynchronously. It has two phases: identification phase and update phase, where we determine if a row belongs to an aborted transaction, and then the update phase restores the latest committed version of the row. Before I show you how logical revert in ADR works, I want to show you how transaction rollback works without ADR enabled. So let's assume we have a couple of transactions using a read committed snapshot isolation level. The first transaction, T1, inserts row R1 in a table T1 and stays alive. And this is the transaction log. Then it inserts another row, and then updates that row with a new value, deletes that row, and decides to roll back. In the meantime, there is another active transaction, T2, that is trying to update a record that is used in T1, which is R1. At that time, all locks are held until T1 rollback completes. And as a result, T2 is blocked. So we use compensation records, as you know, in the transaction log to perform the rollback. So for every record, we have a compensation record. T1 is rolled back. All locks are released, and then T2 is unblocked and completes. Now, let's take a look at the same example with logical revert from ADR. So T1 inserts R1 in T1 and stays alive. Again, inserts R2, updates R1 to R1 prime, deletes R2, and then roll back. And then we have the same T2 that is trying to update the R1 row. You see that T1 is marked as an aborted transaction, and all locks are immediately released, meaning that T2 can go ahead and complete. T2 runs logical revert for R1, as you can see down here. So it brings back the correct version of the row. T1 is rolled back. And then finally, the cleaner wakes up and runs logical revert, cleans up, and deallocates the rows that are not needed. So that is the mechanism behind logical revert that enables instantaneous transaction rollbacks. And finally, the third component, if you remember, of ADR is slog. Slog is a secondary log stream that stores log records for non-version operations, like metadata cache invalidation and log acquisitions. It's low volume because we don't have a lot of records like that, and it's stored in memory. We make sure that we persist on disk by being serialized during the SQL checkpoint. Periodically, we truncate it as transactions commit. And the benefits are slog is a key part to accelerate redo and undo by processing only the non-version operations, and enables aggressive transaction log truncation by preserving the required log records. So you can imagine this is the transaction log, and then there are log records coming in. As soon as we see a log record for non-version operation, log acquisition, we copy that into this slog memory stream. And then on the next checkpoint, we persist those records back into the transaction log. So we very quickly covered PVS, logical revert, slog, and the cleaner. And with all these components and ADR enabled, we get fast database recovery, irrespective of the transaction size, instantaneous transaction rollback, as well as aggressive long truncation. So our diagram now with ADR enabled looks like this. Analysis, the first phase analysis stays pretty much the same, although we reconstruct the slog and copy log records for non-version operations. Redo now is split into two phases. The first phase is completed using the slog, which is much faster. And only the second part is completed by using the transaction log. And you've noticed that it starts now from the last successful checkpoint instead of going all the way back to the oldest uncommitted transaction. At that point, we are able to release all logs and open the database fully. And lastly, undo is pretty fast also because it's completely done using the slog, which contains fewer records compared to the whole transaction log, and goes all the way back to the oldest uncommitted transaction. So this is a quick history of ADR so far. As I mentioned, this has been available in SQL 2019, but now with the release of SQL 2022, we have a couple of improvements on ADR, and these are these. We're introducing a multi-threaded version cleanup, MTVC, where multiple threads will be used if a server has multiple databases with one thread allocated per database. We have many ADR cleaner improvements and efficiencies in how we track and record aborted versions of a page, leading to improvements in memory and capacity. We're reducing the memory footprint for PVS page tracker. We have the ability for user transaction to clean up after themselves if there is a log failure. And finally, we have implemented introducing transaction level PVS, where we are able to deallocate pages even if the ADR cleaner process cannot complete a successful sweep. And that will prevent PVS growth if ADR cleanup is slow or fails. And just to double click into the multi-threaded version cleanup improvement, there are two sort of versions on this, V1 and V2. V1 enqueues database level cleanup work items for the entire database, and V2 enqueues work items to clean up a smaller portion of the database. So to make it a little bit clearer, this is a sample scenario where we have 5 databases and we have configured 10 threads for ADR. If you have enabled only version 1, you will get 1 thread per databases, and cleanup will happen parallelly on the database at the same time. If both of those improvements are enabled, the remaining 5 threads, remember we had 10, the remaining 5 threads will first start cleaning up the smaller portion work items for the database in the order of enqueuing. And if only the second version of the multi-threaded version cleaner is enabled, then all 10 threads act on the cleanup of database 1. Once finished, then it moves to the second database to clean and up all threads and so on. So finally, we are providing monitoring for ADR, obviously, for all these components. You can use DMV's X events to monitor and make sure that everything works as expected, and give you visibility if something goes wrong, so you can go in and troubleshoot. Finally, I want to close Accelerated Database Recovery with a quick demo. In the demo that I'm going to show you, we're going to start 2 SQL Server instances. We're going to bulk insert 5 million rows from a file, and we're going to intentionally crash both of those instances at the same time, and we'll monitor the SQL Server recovery process. Here's the second one also. So both of those SQL instances are up, and we're reading a bulk insert from a BCP file. I'm going to minimize those and explain what we have on the screen. We have 3 charts. The one is the total rows inserted. The red one is with Accelerated Database Recovery off. The green one is with Accelerated Database Recovery on. And we're going to bulk insert 5 million rows and then crash those both of the instances and then start them up again. One big difference is on the transaction log size. You see here the instance with the Accelerated Database Recovery on stops around 500 megs, where the one with the Accelerated Database Recovery off keeps growing because we have this long-running transaction going on. It's the bulk insert. And here the last graph shows you the percentage of the transaction log that we are currently using. So in a little bit, as soon as we reach 5 million rows, we're going to crash them, start them up again, and see how the SQL Server database recovery looks like. So here again, these are the 2 error logs for the instances. Again, very important to see the transaction log with almost 3 gigs with the ADR off, and then with ADR on, we're constantly staying around 500 megs. So for the admins that have a requirement or have experienced uncontrollable transaction log growth, Accelerated Database Recovery is a feature to try on. So we reached 5 million rows insertion. Both of those instances were killed. So I'm going to start them up again. And let's see how fast the recovery. So you see SQL Server with ADR on is already recovered. It took 3 seconds. And as you can see, the analysis was fast as expected. The redo 1238 milliseconds, but the undo is almost instantaneously because we're using that S log to go back and not scan the whole transaction log to complete the undo. So here, if we take a look at the error log, you see that recovery for database in 3 seconds. Here, and then the instance with ADR off is still working. It's at 82. It's getting there. And it's completed. So minimizing those 2 error logs, you see the difference specifically on the undo, because the undo had to go all the way back, if you remember the diagram, to the oldest uncommitted transaction, which in this case was the bulk insert. So with that, over to you, Kendal.
Thanks, Perry. Those are exciting improvements coming to SQL 2022 for administrators. Now let's take a look at what's new for developers. With each new version of SQL Server, we add enhancements and new capabilities to the T-SQL language. And in SQL Server 2022, our language enhancements can be grouped into 3 categories: JSON processing, general T-SQL improvements, and time series capabilities. Included in the general T-SQL improvements category are 5 new bit manipulation functions. We're not going to cover those in this session, so I'll leave it as a follow-up exercise for you to read our documentation to learn more about these. Let's start our tour of the new enhancements with JSON processing, and we'll begin with the isJSON function. IsJSON is not new to SQL Server 2022. Available starting in SQL 2016, the isJSON function tests if a string is a JSON object or array and returns true if it is and false if it is not. It does not, however, differentiate between the two, meaning I can't test if that string is specifically an object or an array. What is new in SQL 2022 is a JSON type constraint argument. With this argument, I can test if that string is specifically an object, an array, a scalar, or a JSON value, which can be any of those 3 plus the literal values false, true, and null. Let's take a look at some example strings, some of which are valid JSON values and some of which are not. And we'll evaluate the results of the isJSON call with and without that type constraint argument specified. Looking at the results, we see that when the type constraint is not provided, anything that's not an object or an array, even if it's a valid JSON value, returns false. With the type constraint specified, we can now tell if that string is specifically an object or an array, or is a scalar value, or one of those values, false, true, and null. So now we have a way with this type constraint argument to test for specific JSON document types. Next, we'll look at JSON object and JSON array. These are 2 new functions in SQL Server 2022. Both return a varchar max, and it contains a JSON object or a JSON array that's created from 0 or more expressions. Both functions also have optional syntax that control how null values are treated. Multiple expressions are separated by commas, and the expressions for JSON object are a key value pair separated by a colon, while the expressions for JSON array are simply the values for each element in the array. The keys and the values for the expressions in JSON object and the values in JSON array can be a literal value, they can be a parameter or a variable, they can be the result of a call to a scalar UDF, they can also be values coming from columns in a table. In this example, I'm combining a scalar function call with a variable and literal values to create some simple JSON documents that are objects and arrays. I mentioned there's optional syntax for how to control null values. And by default, if a SQL null value is passed as the value for a key value pair in the call to JSON object, then it's changed to a JSON null value in the string that's returned. However, a null value passed to a JSON array is omitted from that string that's returned. You can control this behavior with the optional syntax. This is placed at the end of our function call after our last expression. And if we use the syntax absent on null, then null values are omitted from that return JSON string. And if we use the syntax null on null, then the null values are converted into JSON null values and included in that return string. We can also nest calls to JSON object and JSON array to shape our output. And in this example, I'm using calls to JSON object and JSON array as the values for keys to create a multi-level JSON document without having to jump through any hoops with string manipulation or any other complex subqueries. This is a really elegant way for us to create JSON documents. And similar to how the for_JSON operator is used to transform relational data into JSON strings, this next example shows how JSON object and JSON array are referencing columns from the person.address table in their expressions to create a custom JSON string for each row that's returned. And while I could have used for.json to get the same results, for.json does have some limitations. Notice how I've had to use some string manipulation in order to create this JSON array. Also, parameterizing a key name in a JSON object using for.json would require dynamic SQL. So in the end, while I do get the exact same results from both of these queries, it's easier to use JSON object and JSON array to create our JSON strings. With an added bonus, JSON object and JSON array are ANSI SQL compatible, whereas for.json is not. And that brings us to one more new JSON function in SQL Server 2022, and that's JSON path exists. JSON path exists is a new function in SQL Server 2022 that simply returns a true or false value if a JSON path exists within a given JSON string. This example shows the results of JSON path exists testing different paths against a simple JSON string. And as we see, starting at the root, info.address does exist, so the function returns true. However, info.town does not exist, so the function returns false. And info.address with the first element containing a key value named town also exists, so the function returns true. One way that we can use JSON path exists along with isJSON is in a check constraint. If we wanted to enforce that only JSON objects with a specific path could be stored in a column, this example shows that we're creating a check constraint with the isJSON call first checking that the value that's being inserted into the column is a JSON object, and second, that it meets a specific path criteria. We'll try to insert two values into this table. First, we'll insert a value that is a JSON object and does meet the path criteria. Then we'll insert a value that is also a JSON object but doesn't meet that criteria. When we insert our first value, because it is a JSON object and the path exists, the insert happens with no problem. However, when we try to insert our next value, although it's a JSON object, the path doesn't exist. So the call to JSON path exists returns false, which violates the check constraint, and our insert statement fails. This covers our JSON processing improvements that are added to SQL Server 2022. Let's move to our next category and talk about our general T-SQL improvements. We'll start with the functions greatest and least, available today in Azure SQL Database and coming to SQL 2022. Greatest and least return the maximum and minimum value, respectively, from a list of one or more expressions. Where max and min are comparing values within a single column across multiple rows, greatest and least are comparing values across multiple columns within a single row. And in addition to columns, arguments for greatest and least can be literals, constants, variables, or the result of a scalar function, or any combination thereof, as long as all arguments can be converted to the same data type for comparison. And our return type from each of these functions is determined by the argument with the highest precedence data type. In this first example, I'll show the result of comparing a decimal value that's stored in a varchar with a numeric literal, a null value, and an integer that's stored in an nvarchar variable. I'm using sp describe first result set to show the data type for the value returned by both functions. The first thing that you'll notice is null values are not included in that comparison. In our remaining values, 7 was the largest of those numeric values, so it's returned by the greatest function, and 3.1415 was the smallest of the values, so it's returned by the least function. And because these values all had to be converted, and 3.1415 was the argument with the highest precedence data type, our return value is a numeric data type with a precision of 5 and a scale of 4. In our second example, we'll compare string values. And I'm comparing two varchar values against an nvarchar value. And again, using SP describe first result set to show the data type for the value returned by each. Of the three values, Mount Rainier came last alphabetically, so it's returned by greatest, and Glacier was first alphabetically, so it's returned by least. And because the nvarchar data type was the highest precedence, our return value is an nvarchar 13. If we try to compare values where the data types cannot be converted into something that could be compared, for example, numeric values against a string value of Mount Rainier, then we'll end up with an error that gets thrown because they are unable to be converted to the same data type. Finally, an example of how to compare data types using column values. I'm providing the sales quota, sales year to date, and sales last year columns as the arguments to both greatest and least when selecting from the sales.salesperson table. And we see that for each row, we'll return the greatest and least value from those three columns with null values eliminated from the result set. Next up on our list is string split. String split is not new to SQL Server 2022. Recall it was introduced in SQL 2016 and requires compatibility 130 or higher to use, and has two arguments, a string containing a list of values and a single character which denotes the separator between values in the list that we'll be splitting on. What's new in SQL 2022 is an optional third argument named enable ordinal. When the value for enable ordinal is 1, then the table that's returned by string split will have a column named ordinal, which contains the ordinal position of each substring in our list, including empty substrings as we see in this example. Now we can use this ordinal column to extract specific values in our list. For example, if our list contains city-state pairs, we can use the ordinal column in a where clause to return the even ordinal values which correspond to the states in our list. This is a really nice enhancement because we no longer have to use workarounds to guarantee the order of our substrings or to extract a value from a specific position in this list. This is a simple yet really useful addition that will make string parsing much, much easier. Up next, we'll look at date trunc. Date trunc is a new function in SQL 2022, which simply put, truncates a date down to a specified date part. Until now, in order to truncate a date time to a date part, like the current hour or day, we've had to use a combination of cast, convert, format, maybe some date add calls with some math thrown in, which can become difficult to write and to get right. And although these workarounds work, they get complicated really fast. Just try to return the beginning of a quarter from a date time. Thankfully, this is a thing of the past thanks to date trunc. Date trunc has two arguments, the date part, which can be year, quarter, month, week, day, etc., and the date to be truncated, which can be any expression, string literal, column, or variable that can resolve to a valid T-SQL date or time type. This example shows the results of date trunc with each valid date part using sysutc date time, which is a date time 2 data type. Now we have a very easy way to return the beginning of the year, the quarter, the week, the month, etc. for any given date. The data type returned by date trunc is dynamic based on the input date. We'll use SP describe first result set to show the results of date trunc using sysutc date time, which is a date time 2, and get date, which is a date time. And as we see, an input of date time 2 results in a data type of date time 2 being returned, and an input of date time results in the matching data type of date time being returned. If we attempt to convert to a date part that's not supported by the input date, for example, if we try to truncate a time down to a year, we'll end up with an error. And for the performance tuners who might be watching, one more thing to watch out for. Date trunc is a function, and when calling date trunc on a date time column in the where clause, it results in a query that is not sargable. In this example, I've added an index on the order date column to the sales order header table, And when using date trunc in my where clause to look for all order dates that begin at the start of June 1st, 2011, we end up with a scan instead of a seek in our plan. So be careful where and how you use date trunc. Next on our list of T-SQL enhancements, the is distinct from clause. Before we look at is distinct from, let's talk for a moment about comparing null values in T-SQL. One of the many complexities of null values is with equality and inequality comparisons. To show this, we'll look at searching for rows in the sales order header table based on the salesperson ID column. In our sample data set, we see that we have both null and non-null values in this column. Now, it's easy for us to write a query using variables or parameters to find a non-null value with an equality operator. And if that column has an index, as this one does, we may be able to leverage an index seek to find the matching rows, which in most cases is optimal for performance. Null, on the other hand, is considered an unknown value, meaning it's neither equal to nor not equal to anything, even null itself. So equality and inequality operators can't be used in the same way to find null values. So if we know that we have a value in a column that can contain nulls, we have to rewrite our query in order to account for the possibility that we might be searching for both null and non-null values. One way that we could do this is to wrap both sides of our equality comparison with an isNull function. And while this works, under the hood, this introduces a huge performance problem because instead of our seek, we end up now with a scan. To get the seek that we're looking for, we can rewrite this query in another way that combines equality and inequality operators with isNull predicates. And while we do get a seek 2 in this example, the resulting plan becomes more complex, as does the query that we're writing, especially if we add additional nullable columns to filter on in the where clause. And that brings us to is distinct from. Is distinct from is an ANSI SQL standard predicate now supported in SQL 2022. This compares the equality of two expressions and guarantees a true or false result even if one or both values are null. Remember, comparing a null value to any other value, including another null, returns an unknown result with the equality and inequality operators we just looked at. Is distinct from and is not distinct from will always return true or false because it treats null values as known values during comparison. This means we can use is not distinct from as a replacement for equality and is distinct from as a replacement for inequality operators when searching for values which may be null. The distinct predicate can be used in the search condition of where and having clauses, in the join condition of from clauses, and other constructs where a Boolean value is required. To illustrate this, I'll create a simple table with an ID column and will populate this ID column with some null values and some non-null values. And then we'll use is distinct from and is not distinct from to search for both null values and non-null values. Looking at our results, the first result set shows all ID values that are distinct from 17, in other words, not equal to 17, including null values. The second result set shows all ID values not distinct from 17 or equal to 17. Our third result set shows all ID values distinct from null or all non-null values. And our last result set shows all ID values that are not distinct from null, in other words, all null values. Now let's go back to our sales order header example from earlier. And I'll rewrite this syntax, which uses an inequality operator and some is-null predicates, with something much simpler, an is-not-distinct predicate. And using this is-not-distinct predicate, we can search for both null values and non-null values. And what we see is not only is this is-distinct and is-not-distinct predicate easier to write and understand, it also results in a more efficient plan that leverages an index seek in both cases. That's a pretty sweet T-SQL goodie. Finishing out our general T-SQL improvements, let's take a look now at the window clause. The window clause is new syntax in SQL 2022, which enables you to create named window specifications that you can use in the over clause of window functions in a select statement. This is tied to compatibility level 160. That's SQL 2022 compatibility. So you'll need to make sure your database is at the right compatibility level first before you can use this syntax. Now, I've written more queries than I could remember with multiple window functions that use the same or similar definitions. This is a common pattern in reporting queries. And this first example is a simplified version of this scenario, which shows several expressions using the same partition criteria in their definition. This is a lot of cut and paste repetitive code that we can simplify with the window clause. The window clause comes at the end of your query after the where clause and between the having and order by clause. Each named window can define a partition, order, and rows or range criteria for that window. Named windows are then referenced in the over clause. Notice in this example that references to named windows are not wrapped in parentheses, and if they were, the parser would throw an error, but we'll come back to that in just a moment. First, let's execute both of these queries, and we'll see that not only do we get the same results, we also get the same execution plan. And that's because the window clause is just syntactic sugar, which simplifies writing code. Now, expressions in a select clause may also have different window definitions, so we can define multiple named windows. In this example, we've got a sum, an average, and a count, each with different window definitions. Rewriting this using the window clause, we'll create 3 named windows, win1, win2, and win3, each separated by a comma, and then referenced in the select clause. Just as in the previous example, we get the same results and the same execution plan. Notice that these definitions share something in common. In this case, they have the same order criteria. We can simplify this down even more by creating one named window that defines the order criteria, and then we can reference that named window in the average and count expressions, extending the definition of that window by providing the additional criteria after the reference. In this case, when we're extending a named window, we do need to wrap the window definition in parentheses. And as before, we get the exact same results from both queries and the same execution plan. Stylistically speaking, if you prefer to place all your definitions in the window clause, we can write this using multiple named windows, where named windows can reference other named windows and extend their definition. Looking at this same query, this time we'll create win1, which defines the order, win2, which references win1 and adds the partition criteria, and win3, which references win1 and defines the rows to look at. Note that while you can create multiple named windows, you can reference one and only one named window in your over clause. Finally, cyclic references are not permitted and they will result in an error. In this example, win1 references win3, win2 references win1, and win3 references win2. This creates a nonsensical cyclic reference that results in an error when we execute this query. So even though you won't see any changes to performance by using the window clause, it's a welcome improvement that will make it easier to write, read, and maintain queries which use 2 or more window functions that share a common definition. This wraps up our general T-SQL improvements. Let's move on to our last category of language enhancements, time series capabilities. Data is often generated with repeated measurements over time, and we use that data to track changes and trends and build reports where time is one of the axes. Time series data comes from a number of places: stock prices, sales data, sensor measurements, and performance data about your SQL Server instance are just a few examples. Time series capabilities in SQL Server originated in Azure SQL Edge, our version of SQL Server optimized for IoT deployments, and are now coming to SQL 2022 and Azure SQL. The time series improvements consist of a new function, a new operator, and enhancements to 2 existing functions for handling null values. So let's get started with our first new function, dateBucket. Date bucket returns the date part for a given date time corresponding to the start of a bucket for that date part based on an origin date. The origin is an optional parameter defaulting to midnight of January 1st, 1900, and the width of each bucket is a required parameter which determines each bucket's size as that number of specified date parts. For example, a bucket width of 5 and a date part of minute means each bucket will be 5 minutes wide. Let's look at all the possible date part values for date bucket using the current date and time and a bucket size of 1 with the default origin date. And I'll also include the output from date trunc for the equivalent date part so we can compare the two functions. For most date parts, you'll get the same result from date bucket with a bucket width of 1 as what date trunc returns for that same date part. It's not quite the same in all cases though, and date trunc also supports a few additional date part values that date bucket does not. I'd like to pay specific attention to the week date part to highlight this. Today is August 16th, a Tuesday, and the week date part using the default origin date returns a date, which is a Monday. With date bucket, we can provide any valid origin date to define the starting point for bucket calculation, and since January 1st is a Monday, that week date part returns a bucket beginning on a Monday. If you'd like your weeks to begin on a different day, say a Sunday, then you'd need to provide a known origin. January 7th, 1900, for example, is a Sunday, so if we use that as our origin value, then our date parts for week begin on a Sunday. In addition to being able to start at a specific origin, one other way that date bucket differentiates from date trunc is when we need to use arbitrary bucket sizes. For example, if we want to group data together in 5-minute or 15-minute buckets for analysis, as this example shows. Prior to date bucket, we'd have to resort to math or jumping through some T-SQL hoops to group these date time values together in this way. Now date bucket makes this incredibly easy. Now let's have a look at the generate series operator. Generate series is a new operator which, as the name implies, generates a series of values between a start and stop boundary. An optional step parameter specifies the increment between each value returned with the default step value of 1. So as not to clash with any user-defined function of the same name, generate series does require compatibility level 160 to use. The start, stop, and step parameters can be a variable, literal, or scalar expression of any integer, decimal, or numeric data type. Step can be either positive or negative, but can't be 0, and the series begins at the start value and ends when the next step exceeds the stop value. Let's take a look at some examples. First, we can generate a series of integer values between 1 and 10 in default increments of 1. Or we can generate a series of integer values backwards from 100 to 1 in increments of -5. Or we could generate a series of decimal values between 0.0 and 1.0 in increments of 0.05. If the start is less than the stop and a negative step is provided, as in this example, or if the stop is less than the start and a positive step is provided, we'll end up with an empty result set that gets returned. Finally, the data types for start, stop, and step must match each other. If they don't, for example, start and stop are integer data types while step is a decimal, then executing this query will result in an error message. The exception is if the step is omitted, in which case it will default to the same data type as the start and stop values, which still must match each other. Now we'll come back to generate series in just a moment to show how it can be used with date bucket for time series analysis, but first let's cover the enhancement to first value and last value. First value and last value have been in SQL Server since SQL 2012. These analytical window functions find the first and last value, respectively, in an ordered set of values within a partition. What's new in SQL 2022 is syntax for how to handle nulls when each function is computing their result. The new syntax comes before the over clause, and the argument ignore nulls will cause null values within the partition to be excluded from consideration, while the argument respect nulls will include null values. Omitting the argument will result in the default behavior, which is to include nulls. to show the behavior of ignore nulls and respect nulls, I've created a table which contains sample readings taken at 15-second intervals from a sensor. Notice that some of the values are null. We'll look at the output from both first value and last value to show the difference between ignore nulls, respect nulls, and the default behavior if neither is specified. Taking advantage of the language enhancements that we've just learned about, I'm using the window clause to create a reusable definition of the window criteria that I'll then reference for each first value and last value call. Now I'm using date bucket to partition the sensor readings by 1-minute windows. I'm ordering the values within each partition by the timestamp column and using unbounded preceding and unbounded following in the rows criteria to consider all rows within each 1-minute partition when looking for the first and last value. For first value, I'll focus on the first partition. The first sensor reading in that partition, when ordered by the timestamp column, is null. Ignore nulls will exclude that null value from consideration and return the first non-null value, while respect nulls and the default behavior will return null. For last value, I'll focus on the second partition, where the last sensor reading when ordered by timestamp is null. Ignore nulls will ignore that null value and return the last non-null sensor reading when ordered by timestamp, while respect nulls and the default behavior will return that null. Now that we know how null values can be handled in first value and last value, let's bring in generate series, and we'll put all the time series capabilities together and finish by talking about gap filling. When working with time series data, it's often possible that an interruption in data collection results in gaps between measurements in a data set, and it's up to us to help fill in those blanks. To illustrate this, I've got another table which stores sensor readings. This time, the sensor readings are taken every second, and while there's no null values, in some cases the sensor readings were taken multiple times within the same second, and we notice there's also a few gaps of a few seconds between some of our sensor readings. We're going to use a technique known as gap filling to create a contiguous ordered set of timestamps and measurements to help with the analysis of this data. And we'll do so by combining date bucket, generate series, and last value with ignore nulls. We're also going to make this query flexible so that we can analyze the data by grouping readings together into buckets. The final query, which gives us the results, will use several common table expressions. So I'll walk through each of these as a series of steps that progressively build up to the final query. Step 1 is to determine the range of timestamps to generate and the number of intervals or buckets within that range. I'm using the min and max functions along with date bucket to determine the beginning of the buckets that the min and max timestamps fall into. The bucket size is driven by a variable that for now will be 1 to generate 1-second intervals, and I'm using date diff to determine the number of seconds between the min and max buckets. In the sample dataset, there are 15 seconds between those buckets. In step 2, I'll take the query from step 1 and put it into a common table expression. I'll start with that CTE and use cross-apply against generate series with a start value of 0, a stop value of the number of seconds to generate, and the number of seconds per bucket as the step value. I'll add each value returned by generate series to the first bucketed timestamp using date add, which will return a contiguous set of timestamps between the min and max buckets. Step 3 should look familiar. We just talked about last value. So I'm going to use date bucket to group together the timestamps into buckets and last value to determine the most recent sensor reading from each bucket. This does not fill in the gaps though. And that brings us to step 4, where we'll put it all together. I'll take steps 1 through 3 and put them into common table expressions. Then I'll use the contiguous set of timestamps from step 2 with a left outer join to the values from step 3 and last value one more time to impute the sensor values for each gap by returning the last non-null sensor value. The end result is a contiguous set of timestamps and sensor values. Now for fun, let's imagine that we'd like to look at this data in 5-second intervals instead. Because we're using a variable for the bucket size, we'll just change the bucket width from 1 second to 5 seconds and rerun our query to get our results. How cool is that? Well, that wraps up time series capabilities and concludes the overview of T-SQL enhancements coming in SQL 2022. To learn more about SQL Server 2022, we have plenty of resources available for you. There's a lot of great new features in this release, and we're excited for you to try it out for yourself. Thanks for watching, and I hope you enjoy the rest of the Data Platform Summit.